Welcome back to the second part of the Digital Material R&D workshop. In this second part, we will have a look at property prediction on additive manufactured models. For that, we will take one model we created before and do various analysis on it. The goals of this second part is that you will know basic morphology analysis of models with porodict, which means you will be able to extract single pores and their shapes, and also generate statistic of pore sizes. On the right-hand side, we can see such single identified pores in a square gyroid. Other analysis is the physical property prediction, the heat conductivity by conductodict and the electrical conductivity by conductodict, the diffusivity prediction by diffodict, and the determination of the tortuosity by diffodict, the permeability prediction with flowdict, and effective mechanical properties with elastodict. For that, we are now going to start a pore analysis on this squared formed gyroid. In Geodict, all analyses are performed on the currently loaded structure. So if you would like to perform analysis on a different structure, you need to load the structure. For pore analysis on this square gyroid, we had to analyze and porodict. We then select the Identify Pores submodule and we click Edit. We can always make sure to have the default settings loaded by clicking this small icon in the bottom left and then confirm with yes. For this case, we will keep almost all settings the same and just change the result file name to square gyroid. We click OK and we click Run. This identify step will take about 2 to 3 minutes. And like that, we obtained the pore identification of the square gyroid. We can see here the number of pores, which are 302, the number of pore contacts, and also pore volume percentage statistics, information about the sphericity of the statistics of the pores. We can see which gives an estimate of how spherical the pores are. We also get pore diameter statistics. In the algorithm, GeoDict also fits ellipsoids into the identified pores to calculate the pore statistics. And the statistics of the ellipsoids can be found here in this table, where we can see the shortest, intermediate, and longest diameter of the ellipsoids and their minimal, maximal, and mean value. Also the corresponding standard deviation, the D10, D50, and D90 values. All those values can be used for later generating similar structures with a similar pore size distribution. We also obtain a pore orientation, where we can see that the pores seem to be very isotropic oriented. PorePredict also offers a set of different plots, for example, a scatter plot, or a plot where the equivalent diameter of the pores to their volume probability is plotted. And we can also have a look at the pore visualization. Therefore, we head to the Pore Visualization tab and click Load G32. And we click OK. No, the structure should not be set to invisible. And now we can see the identified pores inside of the structure. For better understanding, we can go to Structure tab and clip through the structure. By moving the sliders for the X, Y, and Z direction, the structure is clipped and we can observe the identified pores. We now do the same analysis with a square gyroid. Therefore, we go to File, Open Structure, and we select the cylindrical gyroid from before. We go now back to Edit, and we have to give a different result file name. In this case, cylindrical gyroid. As a short remark, this option, removing the pore fragments at the domain boundary, is often used for CT scans, because in those scans we do not know that the structure is periodically repeating or not. In fact, CT scan structures are in general not periodic, and therefore the boundary pores are removed because they influence the pore statistic, because the boundary pores are cut and therefore smaller. By removing those boundary pores, we get rid of this artifact. We click OK and we click Run. For PorePredict, GeoDict performs a distance analysis of the pores, and based on this distance algorithm, a watershed is applied which finds the identified pores. After the watershed algorithm, pores that appear to be a larger pore are merged back together. Again, this operation will take about 2 to 3 minutes. we obtain the same results as before, and we can even compare those results by hitting the Control key and selecting the result file from the previous run. They are now displayed side by side. For example, we can compare the number of the pores and also the pore diameter statistics. And we see that the cylindrical gyroid appears to have an anisotropic orientation in the Z direction, which is to be expected by a cylindrical object. By clicking Pore Visualization, we can again load the index image of the identified pores, and we click OK. And again, no, the structure should stay visible. And as before, we can go to the Structure tab and slice through it. It's hard to see, but Geodict says there is an anisotropic orientation of the pores in Z direction. For that, we have a look at the result viewer again. And we go to the shape analysis result and click the load comparison of segmented pores and their fits. For that, we click load pore fit shapes. This will load the fitted ellipsoids on which the pore diameter statistics are calculated. And by disabling the view on the volume field, which are the identified pores, we can now have a look at the fitted ellipsoids and clip through those ellipsoids and see that they are indeed oriented in Z direction. For the next part, we are now going to click File and Open Structure. We go to strut-based lattice, one periodic copy, double-click the folder, and click structure.gdt to load the one periodic copy pentamode model again. We go now to identify pores. Give a result file name. And for this case, since the structure is periodic, we uncheck this box. We want to keep the fragmented pores on the boundary, but we also know that the domain is periodic. Therefore, we hit the X, Y, and Z periodicity option. We click OK, and we click Run. we now get a warning that only a single pore was detected. We click OK. And indeed, numbers of pores found is only 1. We have a look in the pore visualization and load the G32 index image. We click OK. And if we clip through the volume field, we see that there's only one identified pore. The reason is that after the watershed algorithm, we can have a look and see the intermediate result by going to the result viewer, intermediate result, load pores from step 1, result of watershed, and we click load GDT. And we see that indeed there have been different pores identified. But PoreOdict also does an analysis and merge pores together, which seem to be one pore but got split up by the watershed algorithm too harshly. In this case, the watershed was not too harshly, but the merging threshold was too harsh. Therefore, we go back to the result viewer and we click load structure to load the pentamode model again. And now we go to identify pores and we click edit. The reason is that this pore fragment reconnection reconnects the pores. In general, using this option is advisable. For this case, we change the threshold to a larger value. If the ratio of the pore size and the area connecting the both pores is larger than 14%, it's reconnected. In this case, we enlarge this threshold to 25 and see if they are still merged to a larger pore. Again, we rename the result file name to thresh25, which is just the threshold of 25. We click OK and run. Now there have been 8 pores detected. If we go to the pore visualization and load the index image and click OK, we can see that indeed all pores have been identified correctly this time. This small example should act as a warning that you can use those 3 options, the domain boundary options, the pore fragment reconnection, and the minimal pore diameter, as a mean to fine-tune the identify pore result. This means if you have a CT scan from which you start, you should first have a small cutout and do a fast identify pore analysis and have a look at the results if they are reasonable. And maybe you need to change the pore fragment reconnection threshold, or you need to change the minimal pore diameter. This option we did not use this time, but it's very simple to understand. It just gives a minimal pore diameter in voxels. Each pore smaller than 2 voxel is ignored. Using a larger diameter means a slower runtime, but in the end, you also might lose information on your pores. Now, we have finished the morphological analysis and we go to the physical analysis. For that, we load the square gyroid again. We can go to File, Open Structure, go into the directory of our project folder, and select the square gyroid. We can also right-click on this project folder and open the project folder directly. Find the square gyroid and drag and drop it to GeoDict. Which option you prefer is up to you. Now, with the square gyroid loaded, we now start with the thermal conductivity analysis. Therefore, we go to Predict, Conductor-Dict, and we select Compute Thermal Conductivity and we click Edit. Again, we choose a meaningful result file name. In this case, this would not matter, but it's best to form a good habit of properly naming your results. In the first tab, the constituent materials, you can see the materials present in the structure. In this case, we have pore material and aluminum, for which we can see the individual thermal conductivities, and we could add a thermal contact resistivity. But for this case, we just need the thermal conductivity, which is taken from the aluminum from the database. We go to the boundary conditions and only evaluate in the X direction the computation. So we uncheck Y and Z and check the X mark. Since this is a triply periodic minimal surface, we can leave the boundary conditions as periodic in each direction. For the solver, we select the LIR solver and we write heat flux into solution file. There is also an additional Equations and Reference tab where you can see the underlying equation that is solved, in this case the heat equation. We click OK and we click Run. The LIR solver developed by Math2Market solves the heat equation and computes the thermal conductivity in X direction for this square gyroid. The simulation is finished in under 1 minute, and we can see in the report the thermal conductivity in X direction, and we could also get the full thermal conductivity tensor if we computed also the Y and Z direction. There are also plots for the temperature, the heat flux, and the convergence of the solver. In the log map, we can also find information on the computation time. If we head to data visualization, we can load the corresponding solution file of the heat flux and the temperature. But for this case, we only want to load the heat flux file. Going to volume field, we can now adjust by thresholding to see where the highest and the lowest flux is. Going to color and visibility, we can also turn back the aluminum to visible. And we now do not see the volume field anymore because the heat flux only happens in the aluminum of the material ID1. Clipping through this material, we see indeed the heat flux solution file is exactly happening only in the material. Satisfied with the thermal conductivity result, we go now to the electrical conductivity. For that, we click in ConductorDict on Compute Thermal Conductivity and now select the other option, Compute Electrical Conductivity. We click Edit, and again, we give a meaningful result file name. Similar to the thermal conductivity, for the electrical conductivity, we also have a tab where we can see the electrical conductivity of the single materials. In the next tab, we can set the boundary conditions. Again, we only want to evaluate an X direction. We still can calculate periodic. We go to solver and select the LIR solver. We also want to write the current density into solution file and at equations and references, we can see the equation that is solved. We click OK and we click Run. Again, the simulation is finished in under a minute, and the electrical conductivity tensor is displayed. The X conductivity can be found in the first entry, and the Y and Z direction of the tensor are not defined because we did not calculate Y and Z direction. We also get the electrical resistivity, and again we get plots of the potential, the current density, and convergence of the solver. And here too, we can have a look at the data visualization and load the volume field. This time we load all volume fields for the current density X, Y, Z, and the normalized current density. We click yes. And when we scroll down on the left-hand side, we can select a different volume field by just double-clicking it. Geodict allows to visualize the current density also in different ways than the volume field. We can decheck the volume field and we can enable streamlines. where we have different streamline settings, like the line thickness, or changing them to streamlets or stream tubes. Or even using arrows. We can turn the structure visible again. And we go to the calculation of the diffusion. Therefore, we go to Predict and select Diffodict. As a side note, if the structure is visible or not does not influence your calculation results, because this is just a purely visualization feed to display or not display the structure. Even if the structure is not displayed, it's still there, it's just invisible. In Diffodict, we stay at Simulate Diffusion Experiment and we click Edit. Again, we give a result file name. And in the first step, the constituent materials, we can see the diffusivity of the single materials, or in this case, the tortuosities. We can set the boundary conditions. We calculate an X direction, so uncheck Z direction. We always can calculate periodic. This is very good because this saves us runtime and also memory. In the solver tab, we select the LIR solver. We could also change the parallelization, but for this case, we want to have the local maximum, which gives us the fastest results possible for our configuration. In the tab, we have the equations for the diffusions. We click OK, and we click Run. While the LIR solver is solving the diffusion equation, we will now receive the diffusivity of the structure and also the tortuosity in a single simulation. We see the relative diffusivity in X direction, and again Y and Z is not displayed because we did not simulate those directions. We also obtain the tortuosity factor and again plots for the concentration and the convergence. We could visualize the data, but for this case, we do not do it. If you are interested in deeper tortuosity analysis, we can recommend you the GeoApp, General GeoApp Property Prediction, where the Compute Tortuosity app is installed. You can click Edit and have various kinds of ways to calculate tortuosities. The geometric tortuosity by using Porodict, physical tortuosity by using Diffodict or Conductodict, mixed tortuosity by using Diffodict, Conductodict, Flowdict, or Artidict, or by using microstructure characteristics with Porodict or Muddict. But for this workshop, we do not do that, just as an information for you. So we cancel this window, and we now head to the permeability simulation. For that, we go to Predict and select FlowDict. We now do a fluid flow simulation, which gives as a result also the permeability of the structure. We click Edit. We give a result file name. As pore, we select as a fluid air. We can collapse and expand by double-clicking it. And then we select air and we click OK. Next are the boundary conditions. Again, we calculate an X direction, uncheck Z direction. And since the structure is perfectly periodic, we can disable this add implicit region and just calculate periodic and here periodic. As solver, we keep the LIR solver, and under equations references, we see the Stokes equation. We click OK, and we click Run. As a result, we again obtain the permeability tensor, which does not feature the Y and Z direction. The permeability can be found in the first entry. We get also the information on the average flow velocity, volume flow rate, Reynolds number, flow resistivity, Gurley value. In the plots, we can see the pressure and the velocity and the solver convergence. Under flow visualization, we could visualize the flow field and also the structure with closed pores. But for this case, we do not need to visualize the results again. For the last step of the second part, we go to Predict and select ElastoDict. Here, we click on deformations and select the effective stiffness option of ElastoDict. This calculates the effective mechanical parameters of this square gyroid. We click Edit, and we give a meaningful result file name. The material information are taken from the material database for Alumino, in this case the Young's modulus, the Poisson ratio, and the thermal expansion coefficient. Under load cases, we select the periodic boundary conditions, and we keep all 6 load cases. What ElastoDict does is that it calculates 3 normal strain experiments in X, Y, and Z direction, and shear experiments in YZ, XZ, and XY direction to compute the full elasticity tensor. At Solver, we use the downsampling option and use a factor of 4. We do that because in this case we would like to have the results a bit faster. Downsampling is making the structure a bit less good resolved, but gives the results faster. At equations and references, the equations that are solved and the references. We click OK and we click Run. If you're more interested in what the solver is doing in the background, you can hit those 2 arrows in the down right bottom, and you can see the iteration the solver does and other log information. While this is calculating, we are going to have our next break and we will be back for the parameter study on an additive manufactured model.